Hello and welcome to the presentation of our contribution to IASS 2021 called Transverse Structural Behavior of Doubly Curved Beam-like Shells, written by Max Dombrowski, Juan Pablo Osman-Letelier, Mike Schlaich and me, Paul Merz. CO2 emissions in general and the carbon footprint of the construction industry are a big topic. As most of you may be aware of, the construction industry is responsible for a substantial share of the overall CO2 emissions. Following this source, it is about 11%. But where in our buildings is the embodied carbon? Over 40% are related with the floor slabs. Therefore, the research and new approach in this field can be a worthwhile investment. Our idea is to use thin-walled, doubly curved concrete shells as a replacement for the conventional and widely applied floor slabs. As shown here, using shells could vastly reduce the concrete demand. So, our motivation is to find out whether these shell structures, which by the way were already built in the past, are fit for wider application as floor slabs, especially as nowadays non-corrosive textile reinforcements, for example as used in carbon concrete, hold great potential for a thin pre-stressed concrete shell system. As you can see in the right figure, the shells are long and not too wide, resulting in a beam-like load-bearing behavior, with pre-stressing only in longitudinal direction. Due to their geometry, also moments in transverse direction arise, which must be carried by the shell thickness alone. The computation of these transverse internal forces is the main topic of this presentation. The computation of the internal force in longitudinal direction is shown on this slide. We can also see the height of the cross-section hy and the longitudinal elevation hx along the length L. As already mentioned, these shells have beam-like load-bearing behavior. Here we see the beam moment and the membrane normal forces, which can be computed using the moment and the area moment of inertia, resulting in this distribution of the cross-section. Projected on the height of the cross-section line, the well-known linear distribution can be observed. The beam shear force is as well directly translated into membrane shear forces, which are linearly dependent on the first moment of area. A shell element of length dx is considered as a curved beam that is continuously elastically bedded by its adjacent cross-sections. This model is used for the computation of the internal forces in transverse direction, which there are the shear force Qsy, the normal force Nsy, and the moment Msy. All the different internal and external forces acting on the element are shown on this slide. We will now go through the different components in detail. First, there is the external load, denoted with Fv1. We will build an overview table of all the different force components and their resulting internal forces in transverse direction. Here we see the distributions of the internal forces computed using the thought model of an elastically bedded beam resulting from the external load Fv1. Next up, there is the change of the membrane shear force, which we computed before using the beam analogy in longitudinal direction. For the sake of increased understandability, the shear force is represented by its components. In vertical direction Fv2 and in horizontal direction Fh. These two are added to this overview with the resulting distributions of the internal forces. The three components shown until now are all independent from the curvature in longitudinal direction. This is where the normal forces in longitudinal direction Nx come into play. It is important to note that there is not only a curvature in transverse direction, but also in longitudinal direction. This can be better seen in a two-dimensional figure as shown here. The normal forces act on both sides of the element in the direction of the shell's central axis. We computed before the horizontal component, so now the vertical component can be obtained using the gradient. The difference of these two vertical components is then to be considered in the balance of forces in transverse direction. As can be seen here, Fv3 is approximately equal to Nx times the curvature kappa. The curvature is linearly dependent on the elevation in longitudinal direction Hx. Therefore, the internal forces in transverse direction are also linearly dependent on Hx, which we will also see later. Now we completed the overview of all the internal and external forces acting on the elastically bedded beam. The component from the longitudinal normal forces Nx results in a positive moment, which as mentioned is linearly dependent on the elevation in longitudinal direction Hx. Our main focus are the moments in transverse direction, and I now want to have a quick check on how they relate to the forces and resulting deformations. The most obvious examples are the two last columns, FH and FV3. FH clearly deflects the edges of the cross-section outwards and down, resulting in compression in the lower part of the cross-section and therefore a negative moment. For FV3, it's the opposite effect. To benchmark our model, we use a finite element computation with the software Sophistic. The results for the different internal forces are shown here. The close resemblance between our computation in black and the FE calculation in gray can be seen. Now I want to come back to the influence of the curvature in longitudinal direction mentioned before and how Hx can be used to minimize the moments in transverse direction. Shown here is the transverse moment for Hx equals 5 cm. By increasing the Hx to 10 cm, we can greatly reduce the moment in transverse direction. But as the transverse moment and Hx are linearly dependent, a further increase in Hx leads to an absolute increase in the moment. The linear dependency is also shown in this graph, where the transverse moment in shell center is mapped against Hx. We also studied some other shell geometries to benchmark our model with the FE calculation. As can be seen, for all geometries, a different Hx is optimal for the transverse moment. This optimization is something we want to investigate in the future. Another important topic is the impact of prestressing on the transverse moment. We are currently working on a journal paper discussing the applicability of these doubly curved shells as floor slabs, which remains our long-term goal. Thank you for your attention, and I am looking forward to the discussion.